So in this video I'm going to be talking about the octal and hexadecimal number systems. They are used a lot in computer science, so are really important. They work in the exact same way as denary, our decimal number system, and the binary number system. If you're not sure how they work, it may be worth looking at my video on that first. So we'll start with octal. Octal, or oct, means 8, like octopus, 8 legs, octagon, 8 sides. So all that means is that the octal system uses 8 digits, the digit 0 up to 7, and is in base 8. So if we think about what that means, it means that we can count all the way up to 7 using a single digit. But if we want one more than 7, we don't have any more digits to represent that. We can't use an 8. So we use the column to the left of it to say that we have counted up to 8 once, and then a 0 to say no more than that. So 1 0 in octal represents 8. So if we had 2 and a 1, that would represent that we have counted up to 8 twice and 1 once. So 2 lots of 8 is 16, 1 more, that represents 17. So we can do the same all the way up to 77. We've counted up to 8 7 times, and then 7 more on top of that. So 8 7 times is 56, add 7, 63. But how do we get up to 64? Obviously we need to add 1 more on, but we can't add 1 more onto this ones columns because we don't have an 8 to record that. So we put that back down to 0, and we add 1 more to the column to the left to show that we've counted to 8 one more time. That of course would bring this up to an 8. So we bring that back down to 0 and put a 1 to the left of that to show that we've counted to 8 times. So hopefully you're starting to see that every digit is 8 times the digit to its right. For example, this column here represents ones, the column to the left represents 8 lots of ones, and the column to the left of that represents 8 lots of ones. So just as we do with the decimal and the binary number systems, we can formalize that using column headings. But this time we're going to use base 8. So this was 1, this was 8 lots of 1, this was 8 times 8 lots of 1, and if we were to carry on, that would be 8 times 8 times 8 lots of 1. So as we did in the previous video, if you've watched that, 1 we can write as 8 to the power 0. 8 because we're base 8, 0 because it's power 0. 8 times 1 or 8 can be represented as 8 to the power 1. 8 times 8, which is 64, can be written as 8 squared. And 8 times 8 times 8 can be written down as 8 cubed. So let's have a look at an example then. If we had the number 372 in base 8, let's see exactly what that means. So starting from the right hand side, we can see we have 2 lots of 8 to the power 0. We then have 7 lots of 8 to the power 1 and 3 lots of 8 to the power 2. So 2 lots of 8 to the power 0, 2 lots of 1 is 2, 7 lots of 8 is 56, and 3 lots of 8 squared, which is 3 lots of 64, is 192. So in total, if we add up everything, we've got 250. So 372 in base 8, which we can use the small 8 down here to represent that it's base 8, is the same as 250 in base 10. So now you know how it works. Test yourself, pause the video and have a go at converting the number 127 in octal into base 10 into our decimal number system. So to work out what 120 or 127 is in octal, we think about our column headings. So we've got 7 lots of 8 to the power 0, 2 lots of 8 to the power 1 and 1 lot of 8 squared, which would give us 7, 2 lots of 8 is 16 and 1 lot of 64. So add them up and you should hopefully get 87. Again, if you didn't get that, have a look back at the video, check your workings, have another go. So now we know how to go from octal to decimal, but how do we go the other way? So if we wanted to go the other way, if we started with 123 and we wanted to represent that as an octal number, we can think about our column headings. So we've got our 8 to the power zeros, which is 1, our 8 to the power 1, which of course is 8, our 8 squared, which is 64, and so on. So we could represent 123 as 123 lots of 1. Of course, we're not allowed to do that, we can only go up to 7, so we can use the column to the left of it, which is 8 times bigger. So we need to work out how many 8s go into 123, and that would be 15 remainder 3. So we can record 123 as 15 lots of 8s and 3 more. 15 is still too big, so we again can use the column to the left of it, which is 8 times bigger, and see how many 8s go into 15. So 15 divided by 8 is 1 remainder 7. So we can record this 15 as one lot of 8 times bigger, remainder 7, and we've still got this 3 here. We can then just check, carry on. 1 divided by 8 gives us nothing, so we can't use the column to the left of it, and we've got our 1 remainder from that 1. So the number 173 in base 8 actually represents the number 123 in base 10. Now the reason I did this last step, because obviously we could have seen that the 1 was small enough, we could have stopped there, but it allows us to use the shortcut. So from the top to bottom in our remainders here, the 371, you can see that that is actually the same as our answer from right to left, 371. So you can actually just use the remainders from your calculations to get your final answer working from right to left. So now you know how it works, pause the video and test yourself. Have a go at converting the number 274 into octal, so 274 in base 10 into the base 8 or octal number system. So to represent the number 274, we need to see how many 8s can go into it. So 274 divided by 8 is 34, remainder 2. We can then take our 34 and see how many 8s go into that, which is 2, 4, remainder 2. Then we take our 4, which we've still got. 4 divided by 8, of course it doesn't go, and you've got the remainder 4. So then our answer here, our remainders here, the 2, 2 and 4, can be used in our answer starting from the right hand side, 2, 2 and 4. So 274 in the base 10 number system can be represented as 422 in the octal number system. So again, if you didn't get that answer, check your workings, have a look back at the previous section and have another go. So the other number system that is really important for computing particularly is the hexadecimal. Hex means 6, like hexagon, and dec means 10, like decagon or decade. So hexadecimal is actually 16, base 16. What this means is that instead of using the 8 digits in the octal or 10 digits as in our decimal number system, we need 16 digits. So we can use our digits 0 to 9 for the first 10 digits of the 16 that we need, but we need 6 more. So what we actually do is use 0 up to 9 as normal, and then from 10 onwards we use letters. So we start with capital letters, going through the alphabet. We need 6 of them, so A to F. So A would be 10, because obviously 0 up to 9 is the numbers. The next number 10 would be represented with an A. B is 11, C is 12, D is 13, E is 14, and F is 15. So just as we did with the octal number system, we can do our column headings, but this time instead of base 8, we are working in base 16. So our base is 16, our first power is 0 because that's the ones column. The next number would be 16 times that, so 16 to the power 1. The next column to the left would be 16 times that, so 16 squared. And if we were to continue 16 to the power 3, then we'd go 16 to the power 4 and so on. So it works in the exact same way, just every digit is now 16 times the number to its right rather than 8, or as in our decimal number system, 10. So if we look at an example, it should hopefully make things a little bit clearer. So if we had, for example, the number 1, 2D, let's think about exactly what that would mean. So we always start on the right hand side. So the D means 13. So looking in our table here, D is 13. So we've got 13 lots of 16 to the power 0. 2 obviously just means 2, so 2 lots of 16 to the power 1, and finally 1 lot of 16 to the power 2. So 13 times 16 to the power 0, which is 1, is just 13. 2 times 16 is 32. And 1 times 16 squared is 256. So in total we've got 13, 32 and 256. Add them up and that should give you 301. So 1, 2, D in the hexadecimal number system is equal to 301 in our base 10 decimal system. So now you know how it works. Pause the video, test yourself, have a go at calculating what 11A in the hexadecimal system would be in our decimal number system. So let's work through the answer. 11A, starting from the right hand side. A, remember, we use for 10. So we've got 10 lots of 16 to the power 0, 1 lot of 16 to the power 1 and 1 lot of 16 to the power 2, which is 10, 16 more, and then 256. Add them up and you should get 282. So now we can do that. Let's have a look at going the other way. So starting with a decimal number and converting it to hexadecimal. So let's look at the number 329 in decimal and try and convert that to hexadecimal. Just like we did with the 8, we want to see how many times 16 goes to it to see how we can write each digit. So if we think about our column headings, 16 power 0, power 1, power 2, we can't put 329 in there, so we're only allowed to go up to 15. So we split our 329, see how many 16s go, and that would be 20, remainder 9. So we can represent that as 20 lots of 16, remainder 9. 20 is still too big, so we split that down, and that is 1, remainder 4. So we can put a 1 in here, 4 in here, we've still got our 9. And then just to finish it off, 1 divided by 16, it doesn't go, and we've still got our 1 left over. So again, we can use our remainders over here in our answer. So from top to bottom and right to left, our answer is 149 in reverse. So we can represent 329 as 149 in hexadecimal. So test yourself, pause the video and have a go at converting 497 in our decimal number system into hexadecimal. So 497, we need to split it down, see how many 16s go. So 497 divided by 16 is 31, remainder 1. So then we need to see how many times we can split this 31 into 16, which goes 1, remainder 15. And then finally that 16 doesn't go, so we're still left with the 1. So 115, 1. Remember, we use an F for 15. So we can write that starting from top to bottom and right to left as 1F1. So 497 in base 10 is 1F1 in hexadecimal. So now you know how to convert between octal, hexadecimal and decimal. Good job, and I'll see you again soon.